Hey, my name is Kerry Cheka. I'm a product expert at Flux, and I'm going to give you a quick tour of a new feature called Copilot. So let's start on the featured projects page. This is a cool repository of a bunch of the public projects that people in the community are working on. It's important to note that all projects that you start in Flux start as private projects, and so no one has access to those except you. And you can choose to make those public. And so people make their projects public. They want to share them with the community. They want to share them with their friends. This leads to a ton of really cool projects being available, A, to look at and get inspiration, but also B, to use as a jumping off point. And so we could go in and look at any of these projects. Say we wanted to make a particular type of BMS, then we could grab this board, fork it, and then start from that project. Maybe we want to remove some of the circuitry there. But anyway, that's not what I want to talk about today. We're going to go through and show off a different use case, which is with Copilot. And so we're going to go into this project. This is an environmental exposure risk meter. We're going to fork this project. And that means it's going to go to our profile. And then we can use it, like I was saying, as a jumping off point. We can take a look at the circuitry that's going on here, maybe edit it a tiny bit. And one of the first things that we need to do is just understand what's happening here. And so this is where I want to show you one of Copilot's cool capabilities that we found at Copilot. What does this project do? Wow, if I could even type. And it's going to think for a bit. Copilot is AI design assistant. It's custom trained by Flux, and it has access to the net list, the components list, the list of parts that you've used on your project, and a couple of other things like project description. And it's going to take all of that information and generate an answer to our questions here. Let's ask it a couple other questions in the meantime, like how would I optimize this design further? How about something crazy like how would I add an analog front end with 10x gain to this design? Let's see what it comes up with. Okay, so we have an answer to our first question. The project is an environmental exposure risk measuring device based on the ESP32 microcontroller, ultraviolet light sensor, and CO2 gas sensor modules. Device measures the risk levels of UV and CO2 exposure to keep users aware of their surroundings. That's pretty cool. The device also includes a voltage booster based on the MT3608, solar panel lithium battery charger with MPPT based on the CM3791 chip, efficiently convert solar energy into electrical energy and charge the batteries. Cool. And so what's really awesome here is that it gave us an overview not only of the function of the board, and it's really cool that it could just look at the chips here and then tell us the general function of this, but it also gave us an overview of how the board is accomplishing that. And so it gives us some information about the architecture as well. So we're seeing that we got a couple more answers on our other questions here. One of the things that I really like asking Copilot is design optimization questions, because those are a little bit harder to get started on. It's not always clear what you want to do and how you would optimize this further. I think especially when you're coming into a design fresh, you haven't really seen it before. You don't totally know what's going on in the design and what you might accomplish. I think this is a really common use case where, maybe you're an engineer at a company that's picking up a design that someone else has completed. Maybe they left or they started a new project and they're no longer accessible. You want to understand the project first, and then you can kind of get started on making it a little bit better. This is a cool way to get a little bit of a head start with that. And so here's some ways that we can optimize. It's suggesting that we look at the power consumption. Maybe we want to simplify the circuits and do a component reduction. That's really good for cost. Optimize the PCB layout, sensor selection. We might want to optimize the size of our modules here. We can check the solar panel versus battery optimization. Maybe we want to change the size of our solar panel. EMI, EMC considerations, routing and signal integrity. Um, these are these are all things that I would do. I think that's pretty good. All right, how would I add an analog front end with 10x gain to this design? To add an analog front end, you need to use an operational amplifier. That makes sense. Choose an op amp suitable for your requirements. Low noise, precision, low power consumption. Oh, cool. Check the supply voltage and make sure it works with the 3.3 volts that's already in your system. Damn, that's pretty nice. No offense to junior engineers that I've worked with, but often I have found that sometimes we have that problem where we're going to choose a part that doesn't work with the current voltage requirements of the system. And you're not going to go and add an entire other voltage regulator just to run one subsystem. It's much more efficient. Well, you could if it's really important, but it's much more efficient in order to just sneak another part in here. We want to use the voltage systems that we already have in place, the voltage rails. Okay, and then it's giving us some instructions here of how we want to connect it. We're going to use a gain resistor, and that's our feedback path. And so we have 9K and 1K for our gain, 1 plus our gain over our feedback. Oh, damn. And then it's also suggesting the analog input of the ESP32, which is IO34. Wow. That's pretty cool. Okay. We can go and do those things. I think that's really cool because a couple of different reasons. I mean, A, it just solved my problem. I was talking to you and I didn't have to think about the things that were happening here. And so, if I was going to go plan out this circuit, I would really have to focus on that. And honestly, I don't keep, even as a professional electrical engineer who's been doing this for 10 years now, I don't just have a library in my head of all of the different circuit topologies and exactly what I need to accomplish in each scenario. I definitely used to when I was doing really in-depth analog design every day. But that's a ton of cognitive load, right? Like that takes up so much memory in your brain. And so the op amp is maybe not the best example of that because I think a lot of us kind of know that off the top of our heads, but you can imagine much more complex circuit topologies here. Like if I wanted to add a filter in this op amp instead of just doing gain, or if I want to do a multi-stage amplifier, this could be really useful. And I got to be totally honest with you that I actually don't commonly remember off the top of my head the position of the resistors in the op amp gain circuit. Like, I remember that there's 2 resistors and one goes to ground, but then I often forget that I'm supposed to use the inverting input for the feedback. Don't at me. I just don't remember that all the time. So anyway, it's just really cool that it can remind us of those things and kind of help us with that. It's cool that it's answering us in text here, but we are working on ways for that to translate into it doing the actual circuit design alongside you. And so you can imagine that if you've asked it to design this op amp circuit for you, then maybe it could just suggest it here. And so then you could either accept or decline those changes, and it could just do it alongside you. And that could be a really, really fast way to do circuit design when you don't have to know a ton of the specifics. Of course, we also have a built-in simulator, and that's something that we're working on over time. And so you can imagine a world in the future where we're prompting Copilot with a circuit example, and we wanted to build this op amp for us. And so it puts down the schematic, and then we use the simulator to verify that live and see that you're actually getting what you expect out of it. And so I think there's some really powerful capabilities that we're just scratching the surface of. So let's go to another example here. I want to jump into a blank project, and let's look a little bit at this blank project use case. So one of the things that's difficult about starting new designs is staring at this blank canvas and being like, what do I do here? I think it's a little bit of decision paralysis. And so, maybe we want Copilot to help us out a little bit with this. Let's say at Copilot, I want to build a design, let's say PCB, that uses a solar panel to charge 6 D-cell batteries. That might sound super contrived, but I was actually talking to a friend the other day, and his blinds work on 6 D-cell batteries, which is outrageous, and I don't totally understand that, but he wanted to make a solar powered charger for this so he never has to worry about finding D-cell batteries again. So anyway, that's why we're looking at 6 D-cell batteries. PCB that uses solar panel to charge 6 D-cell batteries. I want it to, I don't know, collect ambient environment information, like, I don't know, humidity. Let's find out how humid the room is. And send that data over Wi-Fi. Can you let me know the types of parts I would need to do this? And let's see what it says about that. I mean, I think what's really cool is that we can just put in plain English a prompt here, and we don't even have to know exactly what we want to accomplish. I think one of the things that's difficult about electronics design is that you have to start in such a specific place. Like the first thing that I add to the design has to be one of the components that I plan to use, and so I have to search for, like, I have to know that I want an analog front end, or I want, I don't know, like some specific components, like, start with my specific microprocessor. I think it's really hard to jump straight from an idea to that level of specificity. And so it's really nice that there's a step in between here where we can kind of like flesh out our idea in text and then get some suggestions for starting places. Sweet. Okay, so we got an answer here. Let's see what it has to say. To build a PCB that uses solar panel to charge 6 D-cell batteries and collects ambient environment data sent over Wi-Fi, you'll need a solar panel, suitable size and power rating. That's cool. Battery charging and management circuit. Charging a 6 D-cell TP4056. Okay, I'm not familiar with that one, but we'll check it out in a minute. Step-up converter. Oh, very cool. So it's saying if we might need different types of battery charger topologies or voltage converters if our batteries are in parallel versus series. So that's a good thing to note. We'll need a microcontroller with built-in Wi-Fi. That's nice. I mean, we could use a follow-on module, but it's so much easier if everything is in the same package. Humidity sensor, DHT11. I haven't used those, but I have used the BME280. Power supply circuit, passive components, PCB. Cool. I think this is great, but it's saying we want a solar panel and we've got to figure out a suitable size for this solar panel. So why don't we just have it do that for us? So let's see. My friend was in San Francisco, so let's say, what's an appropriate solar panel size to charge these batteries to full in one normal, how about average, San Francisco day? One average San Francisco day probably has a lot of different connotations. So let's see what it's got for us here. I think I've done solar panel system design in a couple of different occasions. One was an off-grid solution that had to last over the course of an entire year. And so what it needed to do was make sure that it would retain enough power through its battery system in order to last through the nighttime, but even in the winter. And so we had to go through a solar panel sizing process that took, I think it was about 2 days. But let's see what it has for us here. Okay, we need to determine the energy requirements for 6 D-cell batteries. Rechargeable nickel metal hydride D-cell batteries, typical capacity around 10 amp hours at 1.2 volts. Okay, so that's 72 watt hours. Average solar energy available in San Francisco is about 5 peak sun hours per day. And then we can determine solar panel size using panel size, energy required, solar hours, 14.4 watts. Okay, that seems plausible to me. So that's pretty cool. I mean, it took me, what, like 2 days. And I'm not saying that this is an incredibly exhaustive analysis. We probably want to go and check this. We want to check out what panel sizes we can actually buy. And so make sure that we have a panel size that's greater than this. We want to check a couple things like, is this true for the winter? Is 5 hours for winter or summer? And then if we want it to work year round, are we going to get too little sun in the winter for this to be true? And so we can dive into some of those design considerations with Copilot if we want to, but I want to jump to a different project here. So let's look at some other use cases. So we looked at how it helps you figure out a design that already exists and maybe how to optimize that design. We also looked at how it can help you get started in a blank design. And what I want to look at here is how we can get started, how we can go through the design process along with Copilot, and how it can help us throughout that entire process. And so we have this example here from Mark Wu, and it looks like this is intending to be an environmental radiation logger. So let's see what we got here. We got an analog input, two-stage gain here. We got a connector, probably for expansion. Obviously, this isn't an entire environmental radiation logger. Probably this is just the start of that, and then it'll build out over time. And we got, what is this, RTC here? Nice. This is a pretty good starting project. So let's look at some of the ways Copilot was used. So looks like we used it here to give us a sense of how to start this project. And so radiation sensor, we have a couple of different options there. It's recommended a microcontroller, the RTC, data storage. So we'll have to do some type of data storage on this project. Some voltage regulator options. And these are probably just example regulators. They may not relate exactly to the project that you're building. And so we can, you can always go in and dive in and ask more specific questions after the fact. But this is just to give you a starting point. So it looks like we've done that here. We asked for a radiation tolerant micro SD card. Cool. Looks like we have some options here like Swissbit. And then we've done a little bit of checking here. So we've used Copilot to help us understand the design and see if there's any errors here. And so this is pretty cool. It can check if we're getting an appropriate power supply. And it looks like we are. We have appropriate decoupling capacitors. Reset pin is not explicitly connected in the provided netlist, but it should have an external port. Oh. That's pretty good feedback. So let's see, do we have N reset here? Yeah, okay. So we have a button, but we're missing the pull-up, so it's able to catch that. That's really nice. And then what about boot? Boot mode selection, connected to ground. Okay, so probably Mark looked at this feedback and connected boot to ground, and then we'll just need to connect this to 3v3 with a 10K resistor. And we can go and check those things. Debugging and programming. Oh, looks like we don't have a programming interface defined, the SWDIO. PA13 and PA14. So let's check those out. PA13. Yeah, we're not using those as a debug interface right now, so that's actually a really good suggestion that probably we'd want to add a connector for debugging this chip as we go into it. And let's look at some of the other ways that Copilot has been used here. So let's check this out. It looks like maybe this is a comment to go through some of the op-amp design. You can use Copilot in a couple of different ways. You can chat with it on the right-hand side bar here, or you can drop a comment and you can talk to Copilot that way. So how can I configure this op-amp to get 100 dB of gain with 20 kilohertz at 20 kilohertz bandwidth while biasing the input at 4 volts? Two-stage approach. Oh, wow. So Copilot suggested this two-stage circuit. 2 gains, 50 dB each. Non-inverting amplifier. Set the gain of each stage to 50 dB. Okay, so it's just going through some implementation details here and was used to help design this circuit. So that's really cool. So anyway, those are just some cool use cases that we found with Copilot. We're really interested to see what you all find, what prompts you all find are helpful with Copilot and which maybe aren't so helpful. We're going to be working on this over time to expand its capability in terms of being able to work alongside you and edit your design with you, and also have access to different types of tools. So we're really trying to expand the capability here over time and make it much more capable at things that maybe LLMs, large language models, aren't quite as capable at now. So we're excited to see where this goes. We would love to see the prompts that work well for you, and also the prompts that don't work well. And so if you have something that you're really excited about, tag us on social media, tag us on Twitter, Instagram, LinkedIn, Facebook, etc. And yeah, we'd love to see what you find. Bye.